Today, we're diving into the story of a chip that completely changed the game for AI. This is the hardware that's been the secret sauce behind Google's AI ambitions for more than a decade now.
So you have to remember, for the longest time we were on this amazing free ride where computers just got faster. Every year, new chips, more speed. But then, all of a sudden, that ride came to a screeching halt. And this happened at the worst possible time, right when AI started needing an absolutely insane amount of computing power.
Yeah, this was a massive crisis. But, it was also a huge opportunity. It forced everyone to think completely differently about how we build computer hardware in the first place. So let's look at the old way, right? Moore's Law. We just sat back and performance would double every couple of years. Easy. But now, in the AI era, whoa. CPU performance might double every 20 years. That's not going to cut it. We couldn't just wait around anymore. These new neural networks were just too hungry, and that forced a really radical idea: specialization.
And this wasn't just some abstract problem. For Google, it was very real. Back in 2013, they did the math and realized that to keep up with demand for their new AI services, they would literally have to double the number of their data centers. That's an insane physical and financial cost. So they were in a race against time to come up with a better solution, and that meant building their very own chip. And that's how we got the first Tensor Processing Unit, or TPU. And here's the key. It wasn't built to be a jack-of-all-trades. Nope, it was a specialist, designed to do just one thing and do it incredibly well: AI inference.
Think of it as being Spartan by design. They just stripped away everything that wasn't absolutely essential for running neural networks. All that complex stuff you find in a regular CPU, like multi-level caches or branch prediction, gone. They traded all that general-purpose stuff for raw, focused performance. Over 2/3 of the chip was just dedicated to pure math.
And the absolute heart of the TPU is this incredibly clever piece of engineering called a systolic array. You can think of it like an engine that's purpose-built for one specific task: the massive matrix multiplications that are, well, pretty much all that AI workloads do all day long.
So how does it work? It's genius, really. It's like a math assembly line. First, you preload all the AI model's weights into this grid of processors. They just sit there. Then, you stream your input data through from the side. Each little processor does a simple multiplication and addition, and the results just kind of cascade down and get collected at the bottom. It's this constant, rhythmic flow of data that makes it so unbelievably efficient.
Okay, so the TPU V1 was a huge success for inference. That's running a model. But that's only half the story. Training an AI model, that is a whole different beast. It's orders of magnitude more difficult, and it was going to require a totally new design.
You see, the TPU V1 was just too rigid. Training needs way more precision, more flexibility, and crucially, you need a way for lots of chips to work together on the same problem. So for TPU V2, they had to go back to the drawing board. They broke up that monolithic design and built something much more modular, something way more powerful.
And you can really see the huge leap they made here. TPU V2 went from a single core to a dual core. It swapped out fixed function units for programmable ones, which gave it that flexibility it needed. But the real game changer? That interchip interconnect. For the first time, they had a super fast way to link chips together and build a true AI supercomputer.
This interchip interconnect, or ICI, arranged the chips in what's called a 2D torus. The analogy of a game of telephone with wraparound shortcuts is perfect. It basically created this super-fast mesh network where every chip could talk directly to its neighbors. And that's absolutely critical when you're trying to get thousands of chips to work in sync to train one massive model.
Okay, so connecting chips on a board is one thing. But what happens when you want to go bigger? Like, way bigger? The next huge challenge wasn't just about the chip anymore. It was about connecting thousands of them across an entire data center.
The problem was that the old way of doing things with rigid copper wires connecting everything in that 2D grid was hitting a wall. It was physically limiting how big and flexible these supercomputers could get. I mean, if one rack of chips went down, it could take the whole system with it. They were running out of road and needed another breakthrough.
And that breakthrough was amazing. The solution was to replace those rigid copper wires with programmable light. They built something called an optical circuit switch, or OCS. It's basically a switchboard that uses tiny little mirrors to steer beams of light, connecting any chip to any other chip. So instead of being locked into a fixed grid, TPU-4 created a reconfigurable 3D supercomputer.
This new optical network just shattered those old physical limits. It allowed them to connect a staggering 4,096 chips together into one single, massive, coordinated system called a pod. And maybe the most incredible part of all of this, the piece of hardware that makes this all possible is just unbelievably efficient.
Get this. That optical circuit switch, the very heart of this light-based supercomputer, uses less than 5% of the system's total power. That is a huge win. It means you get all this scale and flexibility, and you're not paying for it with a massive power bill. That's a core principle of this whole project.
But here's the thing. We've been talking all about this mind-blowing hardware. But that is literally only half the story. The real secret weapon, the thing that makes it all work, is the massive and mostly invisible software stack that's running the whole show.
And look at all these layers. You've got Borg, which is basically the resource manager for the entire data center. You've got the XLA compiler, which is the absolute mastermind that translates high-level AI models into the low-level instructions the hardware needs. Then there are things like SPMD, a programming model that makes those thousands of physical chips look like one giant virtual chip to the developer. This software stack hides all the complexity, which is what lets people train these ridiculously huge models.
So, we've been on this incredible journey of innovation. What are the big takeaways here?
Well, it's really a story of smart trade-offs. They traded generality for way more performance. They swapped out complex hardware for really smart software. And they ditched rigid wires for programmable light to get incredible scale. What this all points to is that the future of AI computing isn't about just one part. It's about these deeply integrated systems where the hardware and software are designed together, hand in hand, from day one.
And that's the key idea. You see this quote, "The software is as much a part of the TPU story as the hardware." That philosophy of co-design, that's the real legacy of the TPU. It's their biggest strategic advantage in this whole AI race.
So it leaves you with this question, right? When hardware and software are this deeply intertwined, who can actually build the future of AI? It proves that it's not just about who can make the fastest chip anymore. It's about who can design the entire system, from the bare metal silicon all the way up to the software that runs on top of it all.